Hi, welcome to Basics of Direct Compute Application Development. My name is Jason Young. I'm a technical lead at AMD. This talk is geared toward those who are new to Direct Compute, DirectX, and GPU computing in general. Today I will be teaching the basics of Direct Compute using an example, matrix multiply. I will be showing a lot of code in detail, and since this is meant as an instructional example, please note the code is not optimal. Don't run and expect great performance. Just learn the basics of direct compute from it. I'll also be doing a walkthrough of direct compute development within the Visual and Studio environment. And hopefully along the way today, you'll learn some general tips on how to develop direct compute applications. Matrix multiply is a basic GPU compute application. Here I have an illustration of matrix multiply. Here, for each element in the output matrix, you multiply a column vector from one matrix with a row of another. I also have here the equation to compute an element in the output matrix. You can see why matrix multiply is a GPU-friendly operation, because every element in the output matrix can be computed in parallel. I want to first start with some HLSL code. HLSL is the high-level shading language for Microsoft DirectX. And this will kind of give you what we need to build on the host side to compute matrix multiply on the GPU. First, I start off with the constant buffer declaration. You can think of this as the parameter data that's being passed from the CPU to the GPU. And here we have the heights and widths of the input and output matrices. Next, I have resource declarations. And for my example today, I wanted to demonstrate different types of buffers being used on the GPU. So here I have a structured buffer as well as a float buffer. Here I declare the structured buffer. It's just a simple float element, so it's not very complicated. That's matrix A. Then I have matrix B, which is a float buffer, and an output matrix, which is a read-write buffer. Finally, we have the heart of the matrix multiply application. The first line defines the thread group size for this function. I declare group size X and group size Y. I will be defining this outside in the host and pass that in when I compile the shader. Next, I have the function. It's a pretty standard loop that performs the multiply. In my example, every thread on the GPU will run this shader, and it maps to an element in the output matrix. In other words, each invocation of the shader will generate a result in the output. So now that we've seen the shader that's going to be run on the GPU, I want to go over the host side API code that you need to write. First, you need to create the device and context for the GPU. Matrix A will be defined as a structured buffer and a shader resource view. Next, matrix B is a float buffer. The output matrix is a float buffer as well, but since we're going to be writing to it, we're going to be using an unordered axis view. Then I create constant buffers, compile and create the shader, and finally execute and read the data back for further analysis. In this talk today, I'll only be highlighting some of the API details, so I encourage you to read more in the DirectX SDK manual for all the details for all the functions. Here, I create the device and the context. Remember that devices handle creation of resources such as buffers and views and shaders. Context handles the execution such as setting pipeline stages and issuing commands. I also wanted to highlight here the creation flag of creating the debug layer. Debug layer is pretty handy when checking for API errors, because if you make an error because you did something wrong, you can see it directly in the output of the Visual Studio. And it's pretty handy. So now I'm going to create the inputs and outputs for our shader here. I'm going to demonstrate first how to create the initial data passed to the GPU. And I'm only going to do this for matrix A. So here we have CPU side code. This is standard C code now, creating an initial buffer, and I'm filling it as standard C code. Then I create a sub-resource data structure, and this is how I pass the data to the buffer, and I just assign it a pointer to the C code C pointer I just created. So this is the first DirectX code used to create buffers. I create a buffer description, and because I'm using a structured buffer, I must set the buffer as a structured buffer. And because I'm using it as a read-only input to the shader, I'm going to bind this as a shader resource. When I create the buffer, I can also pass in the initial data that I created earlier. This is pretty handy if I'm using a buffer that is only accessible by the GPU. So you want to pass in this data so you don't have to do any CPU side copying down to the GPU. Next, I create the shader resource view. Views are the actual mechanism by which a shader accesses a buffer. Because I'm using a structured buffer, I set the format as unknown, so the GPU knows that it must figure out how to read the structured buffer. Next, I create matrix B, and this is, again, a standard float buffer. The difference between the creation of this buffer versus the previous buffer is I don't have to set the structured buffer bind flag. But because I'm accessing the buffer as a float resource, I must set the view format as a single float. So I set that here, and I create the shader resource view. Next, I create the output matrix, and since I'm writing to this buffer, and I'm going to be allowing the buffer to be bound as an unordered access buffer. And then I must create an unordered access view versus a shader resource view, which I've been doing earlier. Again, I must set the format as float. Next, I create the constant buffer. There are many different ways of doing this. I decided here on the host side to create a structure that maps directly to the buffer, the entries I created earlier in the HLSL. Here I create the actual constant buffer. This is similar to creating standard buffers as earlier. Just note the bind flags here. Also, due to the nature of DirectX and the hardware, the buffer size must be a multiple of 16. Finally, I must update the constant buffer with data. Here I decided to fill the buffer directly. So first I lock the buffer with a map call, which returns a structure that contains a pointer to the buffer array. Then I manipulate this pointer as if it was standard C code. So you can see here I cast it to the structure, and then I assign the values. Now I need to compile the shader. I'm doing this directly from with the shader file. So here I have matrixmultiply.hlsl, and I'm using matrixmul as the entry point. This is the function that I'm calling. And finally, I'm using compute shader version 5.0 as the level I'm targeting. Previously, I said I was going to define the group size values outside of the shaders, and this is where I'm going to do that. So here I create an array of the defines for group size X and group size Y, and pass that in during the compilation of the shader. There's an alternative way to compiling a shader, and this is using the FXC compiler tool. This is handy if you want to, say, check the shader without running the app, if you have a formal compilation process, or you're just building the final version of the code. So the FXC compiler can generate the assembly, the object code, or even a header with the object code embedded. This is a call to create the compute shader using the compile shader that we just compiled with. And at this point, all the resources have been created, and we must set them for execution. Views are not set individually, so here I show how to create an array of views, which I then set. So for example, set shader resources, I set an array of shader resources. So this is your input A and input B. I set the shader as well, and the constant buffer here. Finally, I call a dispatch, which launches the number of thread groups on the GPU. So to clarify that some more, dispatch doesn't actually launch a total number of threads, but actually launches a total number of thread groups. So in this example, I have a defined thread group size of group size X by group size Y. That means the total threads in this example would be the width of matrix B by the height of matrix A by the thread group size. Now thread groups run on a SIMD, and if you know a little about the GPU, they're set up as multiple wide SIMD cores. That means when you set the thread group sizes, you generally want to fill the SIMD, something with a size of 64, for example. That means if you have a weird number of thread that you need to handle, then you need to handle these extra threads. So to illustrate what I mean, I have the shaders code that I replicated here from before. And then if you want a generic matrix multiply function, you probably won't fill the thread group with work, all the thread groups. So what I do here is I check the thread IDs to see if they're under the bounds of my output matrix. And if not, I mask them out. So I use a branch here. So at this point, we've completed the execution on the GPU. And then I want to check the results, or usually you want to read the data back to see what it looks like. So because I created my output buffer as only accessible by the GPU, I must create a parallel CPU accessible buffer and copy between the two. So here I have a CPU buffer that I create, and then a call copy resource. And this is the actual call to copy between the GPU buffer and the CPU buffer. And this is similar to doing a memcopy. After that, I most likely want to do something with the output data on the CPU. So here, I do something similar to what I did with the constant buffers. I lock the buffer to get the pointer, and in this case, I'm just printing out the results. So here I want to transition to working with the code. I'm going to bring up Visual Studio and demonstrate some key points within Visual Studio. In this first example, I'm just going to go through the code that we've been working with. So here's the matrix multiply file. I created in a separate file outside of the app here. You should be familiar with this by now. This is the host side code. This is where I create the device. One thing I didn't mention in the talk was that you can check for the device that you create. So here I check to make sure that I'm actually creating a DirectX 11 device. Then I create the buffer resources here, and the matrix I'm going to be using in this demonstration here are actually pretty small and generally not what you want to see when you run on the GPU. Here's matrix A, here's the filling the initial data, here's the buffer description and shader resource view. So I'm kind of skip B and C here, the output buffer, and here's where I compile the shader, and I threw in some code here to check to see whether it built correctly, and you can actually look at the error, and here where I execute the shader, and I check the data. So let me go ahead and compile this and run it. It's going to run in the console here. In my code, I generate I print out the A and B matrices, and in this example here, I created a buffer larger than what I actually needed. So I actually needed only the data in the top left corner, and I did this just to illustrate later on what happens when we vary the thread group sizes. So in this example, I'm going to demonstrate how to use the debug layer. So previously, I've been copying the pbuffer output here, which is the GPU read-write-only resource, to the CPU and then handling that CPU buffer. Let's instead try to access that buffer directly. And so here I'm inserting an invalid call. I build it and execute. So you can see it crashes because I'm not allowed to access that buffer. Generally, you want to handle this better but this is just an example. So here I set a breakpoint, and with the debug layer, I can run to that breakpoint, and then as I step over it, I can see in the output window here an error is generated. It actually tells you what the exact error is. So here I can't access this buffer because it wasn't created with a CPU access flag. So this is very handy when debugging applications to use the debug layer. In this next example, I'm going to demonstrate offline compilation using the FXC tool. So here I have exit FXC. I'm targeting Compute Shader 5. This is the entry point matrix mul and the defines I talked about earlier. So using the tool, I can actually see the assembly generated. Now, as I said earlier, we can also generate a header file. So this header file generated is here, looks like this. So we have the sample code and the object code here. And what you want to do here is include that shader and then create the compute shader directly with that block. So we have that, we compile, and we execute, and we get the same results as before. Finally, in this last example, I wanted to show what happens when you vary the thread group sizes. So what would happen if we hadn't checked for the output bounds here in this shader? So let's comment that out. And I wanted to increase the number of thread groups because generally you want larger thread groups when you're running on the GPU. So instead of 1 by 1, I go 2 by 2. 1 by 1 meant every thread in that dispatch maps directly to a thread on the GPU. So here what's happening is I'm launching 2 by 2 number of threads. And in the dispatch call, I was using actually a small values. So here I explicitly launched the number of groups I need to fill to cover the output matrix. So let's compile that, run it. So you see without doing the checks, I'm actually launching more threads than I needed to compute the output matrix. So I'm actually getting junk values at the end. So this is why we added these checks here in the shader to allow you to generate the correct matrix. So at this point, you've learned how to write a very basic direct compute program. Again, as a tip, read the DirectX SDK manual for more details. And thanks for listening.